Hello friends, in the mathematical probability paper, the first unit is about measure theory. So generally what is a measure? So for example, if you are buying something, if we buy some clothes, then we ask the shopkeeper to give 1 meter of cloth, 2 meters of cloth, like that. If we put petrol to our bike, then we ask for 1 liter of petrol, 1.5 liters of petrol, like that. So measure means assigning numerical values. This 1 meter, 1 liter, 1.5 liters are numerical values. So in mathematics, we know our objects are sets. So with the sets, now we are going to assign numerical values. So measure theory means defining a measure, and we are going to analyze its consequences and properties. So before going to define what is a measure, first we define a Borel field and we concentrate on probability measure. We have a number of measures. We have a positive measure, complex measure, like that. We have a number of measures. In this paper, we concentrate on probability measure. Let omega be an arbitrary space. Arbitrary space means the space may contain any element. We don't know what are the elements of omega. It is an arbitrary space, and F be a non-empty collection of subsets of omega. So consider subsets of omega, and F is a non-empty means the collection F must contain at least one subset of omega. The collection is not an empty one. And we say such a collection is a field if and only if it satisfies these two conditions. The first condition is E belongs to F implies E complement belongs to F. That means for all the sets in our F, its complement. So E complement means omega minus E. Complement of E also in F. That is, F is closed under complementation. The second condition, E1 belongs to F, E2 belongs to F, implies E1, E2 belongs to F. That means the sets in F are closed under finite union. So if we take sets from F, then their union, if you consider finite number of sets, then their union must be in F. So we say a collection F is a field if and only if it is closed under complementation and is closed under finite union. Second definition is about the monotone class. We say the collection F. The collection F is a monotone class if and only if it satisfies these two conditions. The first one is Ej belongs to F. Ej is contained in Ej plus 1 less than or equal to j less than infinity implies union j equal to 1 to infinity Ej belongs to F. That means if you consider a countable collection of sets, this 1 less than or equal to j less than infinite means what? We are considering a countable collection. So this countable collection has an additional property that Ej is contained in Ej plus 1. That is, Ej plus 1 is bigger than Ej. So Ej plus 1 contains Ej. So our sets are increasing one. That is, E1 is contained in E2. E2 is contained in E3. So we are considering a increasing collection of sets, then their union must be in F. Second condition says, if we consider a countable collection of decreasing collection of sets, Ej contains Ej plus 1 means what? The set E1 contains E2. E2 contains E3. That is, the sets are decreasing 1. So, if we consider a monotonically decreasing collection of sets, then their intersection belongs to F. So, we say a collection F, the collection of subsets of omega is a monotone class if and only if it is closed under countable union, provided the collection is a monotonically increasing one, and it is closed under countable intersection provided our collection is a monotonically decreasing one. And we say the collection F is a Borel field if and only if it satisfies these two conditions. Condition 1 says E belongs to F implies E complement belongs to F. That is, if you take any set from your F, then its complement also in your set. This F is closed under complementation. The second condition is Ej belongs to F 1 less than or equal to j less than infinity implies union j equal to 1 to infinity Ej belongs to F. That means if we consider a countable collection of sets, then their union must be in F. So F is closed under countable union. Now we compare the definition of Borel field with the field. The first condition is same. So here also F is closed under complementation, and here F is closed under complementation. The second condition is F is closed under finite union, but here F is closed under countable union. So we can consider a collection of infinite sets also. So a collection of countably infinite sets. So then their union is in F. Now compare this second condition with the monotone class. Here also we are having a countable union, but with additional condition that our collection must be a monotonically increasing collection of sets. But here no conditions. So if we consider any countable collection, then their union must be in F. This is the definition of Borel field.